Now let's discuss colligative properties. Colligative properties are physical properties of a solution that are different from those of the solvent itself. So by adding some solute to the solution, it changes the properties. There are 4 colligative properties that we'll be discussing in this class. What's especially important about a colligative property is that it depends upon the number of solute particles in the solvent, not just if there is a solute, but how much there is. The 4 colligative properties that we will be looking at are vapor pressure, boiling point, freezing point, and osmotic pressure. We'll talk about each one individually, but what you'll need to know is that the vapor pressure of a solution will be lower than the vapor pressure of the solvent alone. The boiling point of a solution will be higher than the boiling point of the solvent alone. The freezing point of a solution will be lower than the freezing point of the solvent alone, and the osmotic pressure will be higher of a solution than it will be of a solvent alone. So let's talk about each one of these in detail so you can understand why they behave the way that they do. So we'll first look at the colligative property of vapor pressure and note that it will be lower when there's a solution. So the vapor pressure of a solution is lower than the vapor pressure of the pure solvent. And importantly, the vapor pressure decreases with increasing concentration of solute. More solute, lower vapor pressure. So let's look at what that means. First off, we need to decide what is vapor pressure. To start with, all liquids have a vapor pressure, and that is the amount of gas that's being emitted off of the liquid. So we are constantly forming gases on top of the liquid, and the more that a substance turns into a gas, the more it's going to have a higher vapor pressure. So things like acetone, nail polish remover, have a fairly high vapor pressure, whereas things like water don't have a very high vapor pressure. Since gas escapes from the surface of the liquid, we're going to focus on that section, and we're going to see that at the surface, of course, the gas can escape. Now let's compare this pure solvent to a solution. When you have a solution, there are solute particles that are mixed throughout the solution, and that includes at the surface. So when a particle of gas tries to escape, it may not be able to escape because instead of a solvent particle being at the surface, there might be a solute particle at that surface, which tells us that the gas will not be able to escape because it's blocked by that solute particle. And since fewer gas particles are escaping, you end up with a lower vapor pressure. The more solute particles there are, the lower the vapor pressure will be because more of those solute particles are blocking the gas from escaping the surface of the liquid. And now let's look at how the boiling point of a solution is elevated over the boiling point of just the pure solvent. So we know that the boiling point of a solution is higher than that of the pure solvent, and we know that the boiling point will increase with increasing solute concentration. The more salt you put in, the more whatever solute it is, the higher the boiling point will be. So what's happening in this case? Well, to understand this, we first need to review what is the boiling point. So boiling point is the temperature at which a solution or solvent boils. And we know that boiling occurs when the vapor pressure of the liquid is equal to the external pressure. That's the pressure pushing down. When we talk about the normal boiling point of anything, we're generally talking about something at 1 atmosphere. So we're looking at sea level because the boiling point does change with elevation. So we're looking at sea level. That means we're going to have approximately 1 atmosphere of pressure pushing down. When the vapor pressure of the liquid that we're looking at is equal to that, then we would have the boiling point of that solution. Now, the boiling point can occur at different elevations with different atmospheres, but we're going to use that as our example. So if I have 1 atmosphere of air pushing down, then I'm going to have a vapor pressure equal to 1 atmosphere for this liquid to boil. So if a liquid is not currently boiling, we need to heat it in order to make it increase its vapor pressure. So that's what we normally do. So if you want water to boil, you have to add energy, heat energy to it so that it will vaporize and turn more and more of the liquid into a gas. And of course, in the case of pure water, we would see that it would start to boil at sea level at 100 degrees Celsius. So what happens when we have a solution? In that case, we will have those solute particles blocking some of the liquid from turning into a gas, just as we saw in the previous area when we looked at the vapor pressure. So we know that the vapor pressure is lower for a solution. So what that means is that we have to heat it even higher for the vapor pressure to be equal to the 1 atmosphere of pressure pushing down. So we have an increase in boiling point because we have to increase the vapor pressure total. And of course, the more solute particles you have, the more it blocks off the liquid turning into a vapor, and that means that the vapor pressure is lower with more solute particles, so the boiling point has to increase. It has to be much higher for the vapor pressure to be equal to the external pressure. You may have seen this effect when you're cooking spaghetti. So oftentimes you'll see on the recipe that asks you to add a little bit of salt to it. The purpose of that salt is slightly for flavoring, but mostly because it raises the boiling point of the liquid to just above 100 degrees, making it cook a little better. If you add even more salt, it will go even higher, so that the boiling point could go up to 110 degrees Celsius, and so your food would cook faster if you add some salt to your water solvent. And now let's look at how the freezing point of a solution is lower than the freezing point of the pure solvent. So we know that the freezing point of the solution is always lower than the pure solvent, and we know that the freezing point decreases, makes it even lower, with increasing concentration of solute. The more solute there is, the lower the freezing point will be. So you already know that freezing means to turn something from a liquid into a solid. The freezing point is the temperature where the liquid turns into a solid. So how do we lower the freezing point? So you already probably know that the freezing point of water is 0 degrees Celsius. And this is where the bonds are starting to form between the two particles of water. So as they start to form, the liquid turns into a solid. In the case of a solution, what happens is those solute particles block the solvent from contacting itself, and so it can't form that solid that it would normally form. Again, more solute particles present will make it harder and harder for the solution to freeze. So the freezing point gets lower. It takes a lower and lower temperature for those water particles or solvent particles to come in contact with each other because they have to push the solute particles out of the way. Interestingly, this makes it even harder for those other parts of the liquid to freeze because the solute is being pushed away from the solvent that is freezing and pushed into the solvent that is not yet frozen. And so it gets higher and higher concentration of the solute, making it harder and harder to freeze. So you'll tend to see that this is like a slush most of the time until you get very, very cold temperatures. So many of you have probably made ice cream or seen how ice cream is made using rock salt. In that case, what they do is they take the rock salt and they put it on the ice, and the more you put on there, the colder it gets. If you put milk in just ice water with no salt in it, you would see that it would never freeze, and that's because the milk has solute particles in it. It is not pure water, so it has a freezing point that is lower than that of water. In order to get that to freeze, we have to add that salt into the ice to make the ice-water mixture cold enough to solidify the milk or cream that we find in our ice cream. Another place you may have commonly seen this is that they salt the road. So in the East Coast or up in the mountains, they'll put salt on the road. And what that does is it lowers the freezing point of the water that would normally be on the roadway, and it's able to melt it. So it starts off as a solid, they sprinkle salt on it, and it melts because the salt is dissolving in the water, lowering the freezing point, making it harder to freeze. And so this is a great way of changing the freezing point by adding a solute. And our final colligative property is osmotic pressure elevation. We see that the osmotic pressure of a solution is higher than that of the pure solvent. And we know that the osmotic pressure of the solution increases as increase the concentration of the solute. So more solute, higher osmotic pressure. But first we better figure out what is osmotic pressure. And to understand osmotic pressure, we need to understand what osmosis is. So first off, osmosis is when a liquid is selectively allowed to pass through a membrane. And in the case of osmosis, the liquid will go from an area of lower solute concentration to an area of higher solute concentration until those two concentrations are equalized. In order to look at osmotic pressure, what we need to have is a container that is split with a osmotic membrane, and on one side we have one solution, on the other we have another. Now, if those two solutions are both the same solvent, the osmotic pressure will be 0 because there'll be no osmosis occurring because there's no difference in the solute concentration. Now let's look at this container where we have the solvent on one side and the solution on the other side. In this case, the solvent is going to flow towards the solution because, again, it's trying to make the concentrations as close to each other as possible. It will never get there because only the solvent can pass through, none of the solute. So it'll never be able to become equivalent, but it will become closer and closer. And when it stops is what we call the osmotic pressure. And what we'll see is that the osmotic membrane will stretch. As it stretches, how far it stretches will tell us what the osmotic pressure is. And again, as there is more solute present, the pressure will get higher and higher so that it pushes out further, trying to get the solute concentration the same on both sides of that membrane. One time that you may have seen osmosis in action is if you've ever noticed earthworms that come out of the soil after a rain. So before the rain, when the soil is dry, the earthworms are fairly small and fine, and as they get wet and they absorb water from the rain, they start to swell up. And that's because the rainwater has less solute particles than the earthworm has in its cells, and so the water is absorbed into the earthworm and the earthworm swells up. Or maybe as a kid you put salt on a snail. If you've ever done that, you've seen that the snail shrivels up. And what's happening in that case is that the salt is pulling the water out of the snail, and so it shrivels up. Again, this is through osmosis through the skin of the snail. This happens to slugs also, and it is used as one of the ways to kill snails and slugs. When you're at the doctor, you may have noticed that when they give you an IV, they give you a saline solution. Saline means it has salt in it. It's got some other things in it too, but it mostly has this salt, and it wants to have the same concentration of solute as what you currently have in your blood. When it has that same concentration, we call that term isotonic because it has the same tonicity or the same concentration of solutes. In this image, we can see that the water is the blue solvent and that the solute particles have a certain concentration. When you have an isotonic solution or a normal concentration, a normal red blood cell will look like it normally would, and the flow of water going in and out is equivalent to each other. It's at equilibrium. On the other hand, if you have a hypotonic solution, say pure water was placed inside the IV bag or the blood cell was placed in pure water, what would then happen is that the water would rush into the cell and the cell would swell and become much larger. And again, that is called hypotonic when it has less than the normal amount of solute. And finally, we can see what happens if we have too much solute. So too many solute particles we're going to call hypertonic. So like hyperactive, it's hyper, it has more than normal, very concentrated solutions. And that's similar to the snail of the salt. And what you'll see is the water will flow out of the cell. And similar to the snail, you'll see that the blood cells will just shrivel up. So it's very important in the medical settings to always make sure that you have an isotonic solution when you're using an IV. Hopefully that helps you understand a little bit more about osmosis.